not understand it theoretically very well. However, most of the most fascinating, or many of the most fascinating states of matter in the universe are due to strongly interacting particles. This includes states, this is in all areas of physics and many other fields. So for example, it includes the quark gluon plasma, which happens a few hundred nanoseconds, microseconds after the Big Bang, and then we can recreate nowadays at heavy ion collisions in accelerators, such as Brookhaven National Laboratory. It includes different phases of matter in neutron stars. Okay, neutron stars happen, as what remains after a supernova explosion, and in these neutron stars, there are many phases of strong interacting neutrons that have very exotic names that we don't understand very well. And closer to, to the subject of this conference, if you have a system of two-dimensional electrons and you apply high magnetic field, you can enter the fractional quantum Hall regime, which is a very highly non-trivial state, topological state of matter, where there is, for example, entanglement between the particles in a very non-trivial way, and where it can give rise to very unusual phenomena, such as fractionalized excitations, all kinds of interesting topological effects and properties. Let me look at this. So now, when we come to strongly interacting, electrons and strongly correlated quantum materials, this is, many classes of materials, where interactions between electrons are very strong and they have exotic behavior. One of, probably the most studied family are the high temperature coupled superconductors, where in a phase diagram of temperature versus doping, we have a variety of phases, few of which we have, a good understanding of, even, after 40 or so years of research. And just to give you an example or just to emphasize, some of the difficulty, if you take a high temperature coupled superconductor, all of the action takes place in these, copper oxygen planes, where at a filling of 1 electron per copper atom, you have a mode insulator. Interactions between the electrons, strong repulsion, prevent them from, they remain stuck in their positions and they cannot move, and therefore they do not conduct electricity. But then an interesting game sort of takes place when you remove a few of these electrons, so we dope with holes. So now, because we have some empty sites here, some of these electrons can actually jump there because they are not repelled by the other electrons. What I mean by that, this electron is not repelled by this electron, there's no electron there. And this creates a motion, as some sites get empty and others get occupied, a correlated motion, which somehow almost miraculously gives rise to high temperature superconductivity. Now, the simplest model that we think describes this physics is due to Hubbard, a British theorist, and it was mentioned yesterday in Oliver's talk. And this Hubbard model, which contains, in the simplest implementation, contains just these, 2 parameters, this, charging energy or energy penalty U to charge, to W occupy a site, and then the hopping between empty and occupied site. I said that we think it describes this physics because we do not actually know. We cannot calculate this model, exactly. You have to use various approximations, so we do not know exactly how to go from this model to these various spaces, or if it actually describes properly all of these spaces. So at least there's no universal agreement, among theorists on how this process works.
Before you change the
Yes.
slides, can you change slide mode? Because Zoom is seeing your screen here, not the screen.
Oh, let me use slideshow. If I swap this place, what does it do? It's I don't want to do that. Can I get it back to
Well, you need to change which window you are sharing. Swap again and then
swap again and then go in
or
Yeah.
share a different screen.
use slideshow? And now I have to
That's good.
make this
It's good now?
small.
It's almost good. Better than before. No,
It-
that's bad.
That's bad? What are you seeing? Are you seeing my eyes?
That just, that would be okay. I think we can do.
No, but this is it. Right?
Yeah, no, this is good. We've got Zoom on the side of the screen.
Oh, Zoom, but that
would.
Now you need to change which screen you are sharing. So go to the screen share.
Okay, let me stop sharing.
Now
and
click
then-
the button and then wait till it shows you several options.
Yes, and I show the full screen.
No,
or the PowerPoint?
just the PowerPoint.
Usually I just do the PowerPoint. But how's this?
No, it should be fine, right? Apparently.
That is good.
Let me hide the floating controls. How's
That's good. Thank you.
that's good? Okay, perfect. So, all right, so we don't know how to go from here to here. I thought you were going to ask me a question about this. I was getting scared. So, very good. Yeah, because I don't know anything about how to get from here to here. So, I don't know anything myself, but I thought no one. So, but I know this is dangerous. It appears in the audience. So, okay, so now because of this difficulty of solving, theoretically the problem of many strong interacting particles, the community has developed alternative approaches to try to investigate physics of strong interacting systems. Yeah? Now, one of the most appealing and one of the most investigated and most interesting ones is to use ultra cold atoms in optical lattices. Yeah? So in the cold atoms community is able to shine lasers at each other, which interfere and create a creative potential, and you can load atoms in this potential. And they have this exquisite knob, called the phase resonance, with which they can tune the interaction, between the atoms, okay? Such that already, about 20 plus years ago, they were able to, change between superfluid and not insulated phases, by this tuning interaction strength between atoms. Okay, they did this with bosonic atoms, so integer spin. Okay, and a few years later, they were able to realize some of this, with fermionic atoms. So they were able to realize the Fermi-Hubbard model. Now, just to give you an idea of some, what is some of the latest, that's been going on in this community, they have been able to realize anti-ferromagnetism in the Fermi-Hubbard model several groups, which means they have these, quantum microscopes where they can load, the atoms, and they can check that at least over short ranges, they have anti-ferromagnetic correlations between the atoms. You see this, blue and gray here. Now, so the cold atoms community is starting to explore, this corner of the phase diagram. Yeah? They would like to explore the entire phase diagram, in particular, reach the region of D-wave superfluidity, superconductivity due to repulsive interactions, but they haven't been able to do so yet. Okay, a major technical difficulty is that in order to get to the region, they believe they have to go down another two magnitudes in temperature in order to go down to these. And they're already working at a nanokelvin, a few hundred picokelvins. So, it's extremely challenging. Okay, there's no fundamental obstacle to doing it, but it's extremely challenging, and progress, has been slow recently in trying to reach those absolute ultra-cold temperatures that they believe are needed to reach these phases. So we have these two sort of traditional platforms, the oldest one, to actually look at the materials, quantum materials, where we have lattice scales, the order of an angstrom, these materials. In these materials, typically we have relatively little control over the parameters of the system. When you grow material, and it is what it is. Okay. Luckily, we have hundreds and hundreds of materials, and we can vary the chemical composition. But the control over the parameters for individual material or device are very limited. Then, the past 20 years, we have these ultra-cold atoms in optical lattices. Here, the length scale is of the order of a micron, and the wavelength of light, and that creates this creative potential. Here, they have exquisite control over all the parameters of the system. However, there have been only a few phases that we have been able to realize. And what I want to tell you about today is about this new platform, called Moiré Quantum Matter. The typical length scale is called the Moiré length, which is of order 10 nanometers. So it's nicely, about a factor of 100 from either of these other platforms. Yeah? So it's a very complementary platform in many aspects. Associated with these length scales are energy or temperature scales. In quantum materials, often energy scales are of the order of 100 or 1000 Kelvin. In the whole atoms, 0.1 nanokelvin. In Moiré Quantum Matter, 1 to 100 Kelvin, which is a convenient energy scale to explore in a solid-state physics laboratory. Okay. Here, we have a lot more control over the system than we have traditionally in quantum materials, not quite as much as with cold atoms, but as you will see, we have been able to realize many, many, many phases of quantum matter.
Sorry.
Yeah.
One might have expected that since the length scale is intermediate
sort of midway between the two. The temperature scale would be midway between the two, and it's
Yeah.
not.
No, they
Is
don't
this
scale
because-
linearly, you know.
Is this because the atoms are neutral? Is that the main difference?
I don't know. I don't think it's because the atoms are neutral. I think it has to do with the scale of the interactions, okay? And these do not scale linearly, okay, with size. So initially, the thing that enabled the development of this platform, this Moiré quantum matter platform, something that we, sometimes the community calls twistronics, which is the fact that with the advent of 2D materials, we have been able to do something which was unprecedented in the history of material science, and that is to vary at will the relative angle between crystalline planes in materials. Okay? So we can take two materials, like for example, graphene, put it on top of graphene, and we can put them on top of each other at any angle of rotation that we want between the two lattices. Okay? This can be 30 degrees, 57 degrees, 1.1 degrees, why not? As I will show you later. And we can do this with absolute control, okay, in very fine increments and in a very reproducible way. And this is something which, when you do this, when you vary the twist angle between two crystalline planes, the properties, the electronic, optical, mechanical properties of the material can vary dramatically. So I'm going to show dramatically with respect to the constituent layers that make this. And I'm going to show you, multiple examples, today and tomorrow. So, okay, so with this platform is called Moiré quantum matter because of the Moiré pattern that occurs, the super periodic structure that occurs when you superimpose two periodic structures and you twist them. Okay, and in the span just of the last 5 years, we have been able to realize almost all phases of matter that we know, from correlated insulators to various exotic superconductors, many topological phases, magnetism, quasi-crystals, ferroelectricity, strange metals, generalized linear crystals, photonic insulators, nematic systems, and the list keeps going, and every month or two, we get one more exotic state of matter that gets realized, often in a very unconventional way. Yeah? So this is something that has sort of exploded exponentially, both theoretically and experimentally. Okay, so this is yeah.
Probably you probably answer my question at the end, but let me ask this question. So if you want to realize one of those physics in real field, and you basically have a lot of different details of that construction of one person. But you start with the Moiré with basically very, very limited degree of freedom. And the question is, how those, so you start with very seductive indices.
Yep.
And you explain those things, how they can be possible.
Yeah. So let me answer that. That's one of the key messages. I was not planning on emphasizing it, but thanks for asking because then I didn't have to say. So, to some extent, usually when you want to get a certain type of behavior, you focus on a particular class of materials, a given chemistry, like you want magnets, you throw some iron, or nickel, or cobalt, and if you want this other thing, you typically have to throw this and that. Somehow, with just one or two elements, in fact, most of these spaces, almost all of these spaces can be realized just with carbon atoms, with graphene, maybe with hexagonal nearby, just with some symmetries. So it tells you that to some extent you can, the complexity of the periodic table is not necessary for all of this. Okay, there's some ingredients, some key ingredients, which are some basic principles which are present, which have to do with your electronic structure and basically the ratio of kinetic energy to interaction energy, which allowed you to actually realize all of this complexity of quantum matter, without having to worry about details of the periodic table, And this is partly because in reality, with these Moiré systems, we create like I will go through this in a moment, but we create some sort of super atom, okay, much bigger in size because of the Moiré scale, which allows us electrostatically, just by dialing a knob, go through the charge states, the valence states of all of these. Okay, so I can, with a tuning knob, with an electric voltage knob, I can go through the periodic table if you want and realize all of these phases, because these phases don't happen all for the same density of electrons. I have to vary the density of electrons to move between various of these phases, but I can do that electrostatically rather than by changing the chemical composition. Okay, So that's something which is very powerful for this platform, you know, and reflects that tunability that I mentioned earlier, or the parameter of the system. The fact that we can change our chemical composition, which means changing the number of electrons, you know, electrostatically.
Related question is very kind of you actually introducing on Harvard. But as far as I understand, Cambridge state questions. The Harvard U is basically a clean number. So this is it depends a lot of something structured, right? Then the question is your degree freedom here is actually the angle and then the size of the structure.
Yes, the angle sets the size of the Moiré wave.
Yeah, the question then is how about the model is right starting point?
Well, so with this, there is a lot of debate in the theory community, and the thing went from thinking of this problem as, you know, multi insulators to realizing that a lot of the physics of this, given the topological structure of the system, I mean, I'm gonna go a bit later about this. You know, you should start, you know, thinking of this more as a quantum Hopf problem rather than. But then there is some shift back, you know, because now we're realizing that there is a lot of local physics also involved. It goes a little bit sloshes back and forth. What is your starting point? You know, you go from here and you get towards here, or you go from here towards here, or maybe there's something in between, you know. And I don't know if Ashwin in his talk is gonna say anything about this, but no, not this time. Okay. But yeah, but there's a lot of back and forth between what is the best point to start and go towards the middle, because it's clear that there's some middle. Tomorrow we'll talk more about that, actually, about the fact that there's both local and internal physics in this problem, you know, in an interesting way. Okay, so with that introduction, I'm going to tell you a little bit about what is magic angle, you know, graphene and magic angle twisted bilayer graphene. I'll tell you and about, you know, our discovery, and then the rise of Moiré quantum matter, or what have been some of the experimental developments since, very quickly. Then I want to spend a few minutes telling you about Moiré magic beyond graphene. You know, usually a lot of people are focused on graphene, but there are many other systems. Transition method chalcogenides, hexagonal boronitride. So I'll tell you a little bit about Moiré ferroelectricity in bilayer graphene. This is quite simple. Tomorrow I'll tell you about some much more complex type of unconventional ferroelectricity that we have recently discovered. And then I'll end with a little bit of an outlook of, you know, this is extending well beyond what you know, condensed matter, quantum electronics, you know, community is doing, you know, to many other communities. I'll mention a few words about this. Okay, so graphene is a sheet of carbon atoms, okay, honeycomb in a honeycomb structure. All of these atoms are all carbon, so they're chemically the same. But from the crystallographic point of view, we have two inequivalent types of carbon atoms. We call them A and B sublattice, or the red and green balls here. And that's because to tile a honeycomb, you need, you know, two unit vectors plus a two-atom basis. Okay, to tile a honeycomb. Now you can calculate the electronic structure of electrons in graphene, a simple model. Okay, and you get energy versus momentum in the x and y direction. Okay, and it's this very unusual electronic structure where near the Fermi energy, you have a linear energy momentum dispersion. Okay, that's unlike most, you know, solid state systems where you have a quadratic or parabolic energy momentum dispersion. And this, you know, already from the beginning of graphene led to all these analogies between electrons in graphene and massless, you know, ultra-relativistic particles in high energy physics. In fact, the equation that describes the behavior of electrons in graphene, the Fermi energy, is the Dirac equation in 2 dimensions for massless particles, okay? Where you can see here energy is linear in momentum, and this, you know, which is in the usual Dirac equation, is a spinor which tells you whether the spin of the electron is up or down. Here is a pseudo spinor which tells you whether the weight of the electron wave function is on the A type of atom or on the B type of atom. Okay? Now, the only other thing that I want you to know about electrons in graphene is that we have two inequivalent, you know, these double Dirac cones, which we call valleys. We have two of them. We call them the K and K prime valleys. The others are copies of the typical space lattice vectors. So we say that electrons in graphene have this, you know, fourfold degeneracy, you know, I mean, spin up, spin down, or valley K prime. Just remember number 4 because it will appear later. Okay. Okay. So if you put graphene on top of graphene and you know, rotate the angle, you have the form of Moiré pattern. Okay, this usually goes continuously, somewhere in zone, so. But where the Moiré wavelength, the distance between the soccer balls that you see in the screen, is, you know, roughly inversely proportional to the twist angle for small angles. Okay? The Moiré wavelength can go all the way to infinity because these two lattices are identical. If you have two lattices which have a different lattice constant, such as graphene and hexagonal nitride, then the Moiré wavelength saturates to a maximum value depending on the difference between lattice constants. Okay, so nowadays you can get also Moiré physics and Moiré quantum matter with two different lattices, even if they are at zero twist angle. You don't need to twist them necessarily. Okay? Okay, so this is what happens in real space when you put graphene on top of graphene. So what happens in reciprocal space and what happens to the electronic structure? Okay? So here we have a single layer of graphene, the electronic structure. We zoom in into the Dirac cones near the Fermi energy. This is, the Brillouin zone. Here we have, these are the Fermi disks that appear if you chop at a certain Fermi energy. Okay, we have the K and the K prime. Now, if we put another graphene sheet and it's exactly aligned with respect to this one, okay, then the reciprocal spaces are exactly aligned with each other, okay, of the two. Now, if you rotate in real space, you rotate by the same angle in reciprocal space, okay? So that means that if you, this, connections with something so slow, but if you rotate by a certain angle, in momentum space, you also rotate, and therefore the Dirac points of your two, Dirac cones of graphene sheet 1 and graphene sheet 2, they separate in momentum space, yeah? And they separate with something proportional to the sine of the twist angle over 2. Yeah? So for small twist angles, the separation in momentum is proportional to the twist angle. Okay, so twisting leads to Dirac cones separating in momentum space. Let's start from a relatively small twist angle and let's see what happens. Okay, so this is the situation. Okay, when you have here the Dirac cone from graphene sheet 1, the Dirac cone from graphene sheet 2. The angle is small, so the separation between the Dirac points there, or charge neutrality points, is proportional to the twist angle. This would be the situation, the electronic structure that would be realized if electrons in one graphene sheet would not be aware that the other graphene sheet exists. Okay, you would just interpenetrate the dispersions. However, when we put graphene on top of graphene sheets are just 3 angstroms apart. So the electrons are very much aware that the other graphene sheet exists, and in particular, they can tunnel between the two sheets. Yeah? So that leads to band repulsion here at the crossing point. Okay? I'm sorry that this projector rush we will see it. Okay? This is exactly the same thing as bonding antibonding states in a hydrogen molecule, but these are bonding antibonding bands in a giant graphene molecule. Okay, molecule. Now the situation that I'm showing here is when this interlayer tunneling, okay, is smaller than the energy of that crossing point. Okay, we have band repulsion. The system pushes one of the bands down a little bit. Okay. Now, if you keep decreasing the twist angle, these Dirac cones are going to get closer and closer and closer, and this band, which at the crossing point it's getting pushed down, gets pushed down more and more and more until at some point it touches 0. Okay, that condition is called, when 2W is about the energy of that crossing point, we'll reach a flat band condition. It's called, okay, and that flat band condition is reached at an angle which this Twister and McDonald coin as the magic angle, which happens to be 1.1 degrees for graphene on top of graphene. This depends on that interlayer tunneling. Different materials for different graphene structures, etc. Yeah?
Sorry, can you repeat what is the condition? Because in the plot, I still see 2 points.
Well, there is because that's right before you reach the flat band condition.
So they actually touch and form a line.
The band, I'm going to show in a moment. This is schematic. I'm going to show calculation in a moment. Okay. Now I should mention that. So there was about 13 years ago now. So there was interesting work at the single particle level. Okay, at this prediction of these flat bands, both by Twister and McDonald, also by Suarez, Moiré, and collaborators, and the group of Eva and Drake had experimental. They had done scanning tunneling microscopy on twisted binary graphene, and they had seen there's a Franck singularity associated with this region here, and they had seen that the energy of that Franck singularity goes to 0 at about 1.1 degrees. So there was already, about 13 years ago, a lot of interesting at the level of single particle physics work that something is happening at this magic angle. Now, so this is a cartoon. This is an actual calculation of the electronic structure. Okay, energy versus momentum. These are the flat bands. Okay, this is for 1.1 degrees, and you can see they're not mathematically flat, perfectly flat. There's a little bit of dispersion, but this, is orders of magnitude flatter than the original Dirac cone in the graphene electron structure. These are the other, remote bands, you have many of them because of this folding process, okay, because of the Moiré itself. Now, flat in momentum space, if we try to go back to real space to see where are the electrons, when they're in these flat bands, where do they like to be, okay? You have to do Fourier transform, and the flat, and the Fourier transform of a flat object is a highly peaked object. Yeah? So if you look in the actual twisted bilayer lattice in real space, where do the electrons like to be, okay, when they're in this flat band? They like to be in regions which are what we call of AA stacking, where locally it appears that all of the carbon atoms are on top of each other in the in the twisted structure. Of course, because there is actually small twist angle, when you, laterally move a little bit, you go into regions where, due to this out of registry, because of the twist, the atoms are going to a locally AB or BA stacking configuration. This is the natural stacking configuration in graphite. Yeah, and the electrons like to be in these AA regions, and they do not like to be in the AB or BA regions. Yeah? So schematically, magic angle twisted bilayer graphene looks like this. These are, there are regions of AA stacking where the electrons like to be, and regions of AB and BA stacking where the electrons do not like to be. Yeah? In a slightly more realistic schematic, magic angle twisted bilayer graphene, you have these regions of AA stacking, which I shaded in yellow. These regions are spaced by about 13 nanometers. Okay, and then the regions in between are regions of ABA stacking. The electrons like to sit in those regions. Okay, this is going to be the analog of a triangular Fermi-Hubbard lattice in cold atoms. Okay, however, I put triangular in quotes. The AA sides form a triangular lattice, but AB and BA is not the same. So this is actually a conical structure in reality. And I put Fermi-Hubbard in quotes because due to the, this structure has very interesting topological properties in the electronic structure, which prevents the direct mapping to the usual Fermi-Hubbard lattices of cold atoms. Okay? But, you get the idea, electrons there. Okay.
So, sorry, just to make clear, so the real space picture of this magic angle is when you get these regions of perfect stacking, and if I were at 1.2 degrees, I wouldn't find anywhere where they really land.
So these AA regions, okay, this structure locally, that is at any small angle. When you get to like 30 degrees, it becomes sort of the carbon opposite crystal, which does not clearly show these AA and AB regions. Okay, so but for any small angles, for 0.8 degrees, for 1.5 degrees, you also have these regions like that. You don't have these very flat bands. Okay, the band. There is a continuity. I have a video which I could have shown with the evolution of the electronic structure as a function of twist angle. Okay, and you got you go from Dirac cones, and then maybe around 2.5 degrees or so, these Dirac cones start to experience a serious renormalization of the velocity. Okay, but then it becomes dramatic in the vicinity of 1.1. Like from 1.3 to 1.1 is a dramatic flattening, and then below 1 again it changes. You go out of the flat band condition, so to speak. So all the magic, as I will show, happens roughly between 1 and 1.2 degrees.
A follow-up from that. Can I think of this in real space as a sort of destructive interference condition? Like if I wanted to try and delocalize these barrier functions, I can do it at most angles because I can go through different layers, but then there's a magic angle where those destructively interfere and I really get stuck. So
there is a way of thinking about how do you get the flat band condition, which has to do with interference. Okay, basically interference in the tunneling process. This magic angle condition, you can think of it as it occurs when it is as likely for an electron to continue going through its own layer as it is to tunnel to the other layer. Okay, and there is something in terms of interferometry that of interference that you can think of to think of this flat band. Yeah. Okay, so. Now, how do we make these devices? Okay, so it is both simpler and more complicated than you might think, naively. Okay, but conceptually it's very simple. Let me just show you. So we start with a glass polymer which has a a glass slide which has a polymer stack attached to it. Yes, with at the bottom of the sticky layer. Then we bring a substrate which has hexagonal boron nitride on it. The silver nitride is a layer material also, but in this case, I'm going to use it as just as a nice inert substrate, high quality substrate. This is about maybe 10 nanometer thick, something like that. Okay. I pick it up with this sticky polymer, okay? And then, sorry, again, it goes very slow because of Zoom for some reason. Then I bring another substrate, okay, which has graphene on it, okay? A monolayer of graphene on it. Yeah, this, thousands of groups around the world can do this. The interesting thing now is that I position my HVN flake stuck here, sort of halfway on top of this graphene flake, okay, this graphene sheet. And I go down and I tear, I pick up half of the graphene. Yeah? Now this graphene sheet is a single crystal, and that means that the atoms here on this upper part and the atoms here on this lower part, even though I've tear these two structures, they're still correlated in their orientation and their position. Okay.
This just happens naturally, so it just sticks to the HVN.
It sticks to the HVN and you tear it. Yes. Yeah.
And the bottom is also HVN?
No, this is graphene. This is graphene. The bottom here is silicon oxide. Typically silicon oxide. Yeah. Okay. So then, from the top view, I have my substrate with half of the graphene, and then I have the glass slide with the polymer with the HVN and the other half of the graphene there. Okay. Now I can rotate the substrate by any angle that I want, for example, 1.1 degrees. Okay. And then I translate it on top of the other. Yeah. And now I stack it. I place it on top. And I pick it up. Okay. And then I can continue doing fabrication, etc. Okay. Amazingly, this very simple process is literally like this, and we do it in ambient conditions, produces this very high quality molar structure, which is going to show all the data that I'm going to show there. Yeah.
I was wondering, now over years that you're doing this, what's the yield to do now? What that superman, for example?
It depends very strongly by group, even by graduate student or postdoc, not all equally skilled. In my group, we happen to have a extremely high yield. For 2 linear devices, it's about 2/3. Okay, so most of the time, for 3, 4, 5 linear devices, it's 100% pretty much. Every device, we have more devices we can measure. But I know that for other groups, it's 1 in 100. So other groups suffer a lot in terms of yield. Okay. But I have hosted many groups and their yields have improved and so on. In fact, I'm planning a workshop next year to help groups, do this more. Somehow we do something, we're not exactly sure what we do, which is different when we have such a high yield. We started, of course, much earlier than anyone else, but there's some secret ingredient that we're not aware and very sure. But people are improving in their yields, over time. And there are now several dozen groups that can do this regularly.
A technical question, I guess your lens are very tricky, but nevertheless, if there is vibrations and also some of the fluctuations, and those can be critical in having exact angle and positionings.
We have very high quality nanopositioners and tables and so on to position these structures and very accurate temperature controllers, for the various processes. It's a little bit more involved than what I described, okay? Not much more, but a little bit more. And when I visit sometimes other people's labs, they don't have the same quality of machinery. Okay? But even people that have very high quality, but I mean, to some extent, it's also how many people are doing this and how many people are, in most labs is a couple of people, but in my group, the whole group is doing this thing. So at some point, we realized for one of the earlier generations, we're now in our 5th generation of stacker system, but generation 2 or so, we realized that we had to aim at 1.3 degrees, and then we would get them at 1.1 because there was in the mechanical process, there was like a thing, that made it, and then only if you make many devices, you realize of these things, you try twice, and you're like, oh, it's off. Oh, it's not working for me. You make many, you realize the key little, things that you have to do. And of course, that's very dependent on the device. Okay. Yep. Yes, of course. So we're doing this under a microscope. So you pick up this flake with the HVM, and then you know exactly what's the relative angle between this and this, okay? Because you didn't rotate in between. So now we literally do that thing. We rotate 1.1 degrees, we translate, and we put it on top. Yeah, it's not like you take one piece and then the next day a piece from another place, or yeah. Yeah, no, we have very rigid positioners. When we do this thing, the angle doesn't change. So as I said, for this thing is extreme, it's very sensitive. This thing works between, the magic happens between 1 and 1.2 degrees more or less. So you have to have micropositioners and goniometers and everything that is stable on a 0.01 degree scale to get this thing reliable. But that's not, it's not like exquisite engineering. You buy commercially off the shop things and they have that accuracy.
So how do you do it just having HBM? You don't have this like reference,
Sorry,
if you're stacking HBM with graphene, how do you know?
so the angle between this and this, for this process that I'm describing here, it doesn't matter. Okay. Nowadays, as I will show tomorrow, we do structures where it matters, and then we have to use other techniques to determine what's the relative angle between the HVN and the graphene. But for this process, it doesn't matter. We just use HVN as a substitute.
Yeah, I meant the link. I guess we'll talk about it.
I mean, when it matters, okay, when I want to align the HVN to the graphene, for example, we do second harmonic generation to determine the crystallographic axis of the HVN, and then we choose straight edges. We choose graphene flakes with straight edges, and then we position the HVN and hope that the straight edge of the graphene is a crystallographic edge, either armchair or zigzag, depending on what we exactly want to do. Okay, and that's how we align them. Any other questions? Same question? Yeah, I'll talk a bit more about alignment to HVN tomorrow. Okay. Okay, very good. So then we continue doing fabrication in a very standard way, and we end up with a device that looks like this. We have twisted bilayer graphene, okay, at any angle that we want, for example, the Magiac angle. It's encapsulated in HVN top and bottom. Okay. We can contact with source and drain electrodes so that we can apply a voltage and measure a current through it. And then we have these 1 or 2 gates, okay? We have these metallic plates with which, the form a parallel plate capacitor with the graphene, okay? Yeah. Twisted bilayer graphene is 1 plate of a parallel plate capacitor. This metallic electrode is another plate of the parallel plate capacitor. So I apply a gate voltage, I apply a voltage, and I can vary the charge density in the plates of the parallel plate capacitor. That's how we vary the charge density in the twisted bilayer graphene, okay? And because the Moiré structure is a large Moiré structure, we can do with electrostatics vary a substantial fraction of electrons per Moiré unit cell, okay? Because it's a very diluted system. We would need 3 or 4 orders of magnitude higher electric field if we wanted to change, a regular material, metal. It's number of electrons are pressure.
Fabricate that device, the bottom there, like gate and so on, you do it in the clean room, and then you just bring what you have made before and then just stack them.
That's right. We have we call it the stack, which is the VM twisted bilayer graphene VM structure, and that thing is on a substrate, and then we go to the clean room and we fabricate. The bottom gate can be a metallic gate or it can be a graphitic gate. So if it is a graphitic gate, you have to do extra stacking. We often have a top gate, which can be a metallic gate or a graphitic gate. If it is a graphitic gate with dual gate graphite, then you have to have graphene, HVN, twisted bilayer graphene, HVN, graphite. So it's a multi-stack process. I will show tomorrow. We do now magic angle pentalayer graphene, with 5 layers twisted. Then we have 8 or 10 stacks process there. So it requires patience, graduate students, but it's doable.
But my question is, does this bilayer graphene see all these?
No,
processes
because it's embedded in the HVM. The bilayer graphene is happy there, not seeing all the polymer lithography, resist, etching, all those things. Okay.
So it is going through the process, but it is not.
It's not experiencing it because it's isolated by the HVM.
question for you. In the gate, do you know anything about what the electric lines force doing? Naively, you'd have a simple capacitor. They go straight up and they're perpendicular, but you might have the possibility that there are screening forces and they bend and focus. Do you have any notes?
This is not really to scale, right?
Yeah.
I mean,
Right.
this thickness is 10 nanometers and the device is microns. So for the most part, straight up electric field lines. Okay. At the edge, it's true that you can have some bending in the same way edge effects in any capacitor you would have. Okay. But that's a tiny portion of the sample. Okay. There are devices on which we and the community has investigated those effects in homogeneous density profiles near the edges, etc., especially when we had thicker dielectrics, okay, of order set of 100 nanometers.
But what about periodic profiles within the Moiré? The possibility that the electric field lines focus in towards the Vanier states. and have
Oh,
a
towards
periodic
certain
state.
regions and not others and so on. So for example, an experiment that some people have done is when you use graphite gates, okay, when you apply a large magnetic field, then you have, if you have thin graphite gates, you have lambda levels in graphite gate, and you can have an inhomogeneity in your gating. You can see oscillations which have nothing to do with oscillations in your sample, but have to do with oscillations because your gate has an oscillating density of states because of the lambda levels in the graphite. These kind of things people have thought, okay? That one in particular that you say, oh, because my AA sites, the electrons like to be there and not in the other region, you're going to have some, electric field lines going this way or that way. I don't know if anyone has considered that, okay? Right now, off the top of my head, I'm not sure. I haven't thought about that. Okay, so, I'm going to start showing data. Let me remind you how conductance of regular graphene is, okay? So in regular graphene, the conductivity versus charge density, looks like this. If your Fermi energy is deep in the valence band, you have lots of holes and you conduct very well. If your Fermi energy is deep into the conduction band, you have lots of electrons and you conduct very well. If your Fermi energy is at the charge neutrality point, you have very few charge carriers, so you conduct poorly. Okay, so conductivity versus charge density looks like this V shape in graphene. It's measured by thousands of people. Okay, this is how conductance versus charge density. This is the previous was in a schematic. This is actual data. Looks like. Yeah, you can see that near charge neutrality, this is still V shape. The system remembers it comes from graphene. Okay, but then you have all these ups and downs, all these craziness. Okay, so let me guide you through this. So this is again the electronic structure. Okay, and remember that I told you that number 4 would appear again. Turns out that in these black bands, starting from charge neutrality, to reach this region, you have to add 4 electrons per Moiré unit cell, okay, to the system. From charge neutrality to reach this region, you have to add 4 holes per Moiré unit cell, or remove 4 electrons per Moiré unit cell. And so these black bands contain in total 8 electrons per Moiré unit cell. Okay. When you put the chemical potential here by adding 4 holes per Moiré unit cell, this is a single particle gap. Therefore, you have 0 conductivity. You have a single particle insulator. Okay. In reality, interactions modify these things and so on. But to see the further, that's how we understand this. Okay. This is the same thing, 0 conductivity if you put 4 electrons per Moiré unit cell because you reach that single particle gap. Okay. The funny thing that happens is if you put 2 holes per Moiré unit cell or 2 electrons per Moiré unit cell, now your chemical potential is in the middle of a band with a very high density of states. It should be a very good metal. Okay. However, you have an insulator. Okay. That insulator is a correlated insulator, which happens at 2 or holes or 2 electrons per Moiré unit cell. That was in the initial discovery. Now we know this happens also at other integers of electrons per Moiré unit cell. Okay. So that was the discovery of correlated insulators.
Just asking a question here. How do you know this is a correlated insulator and that the theorists haven't just screwed up on the band structure?
So by now, the theories if they screwed up in the band structure, they continue to screw for the following 5 years when thousands of theories look at this. There's a possibility that they continue to screw up with the band structure, okay? But this thing is actually relatively, I mean, I shouldn't say this, you know, at some level, it's a very relatively simple system. It's just graphene on graphene. And we know the individual components to death, you know, like very well, okay? Now, it is true that it's not as simple as people initially thought. You know, this Mr. McDonald model, you know, is, you know, in reality, you have now a solid with a 10,000 atoms unit cell, okay? Which people cannot calculate very well, you know, because it has 10,000 atom unit cell plus orbital. So you have, you know, it's hard to calculate the actual electronic structure without doing simplifications of the type, you know, the continuum model that Mr. McDonald did, etc. So it's a subject of active research now, calculating accurately the electronic structure of twisted bilayer graphene and other Moiré systems. For example, there are things like relaxation effects, okay, which initially were not taken into account in the Mr. McDonald model. If you don't take that into account, those relaxation effects, you do not have the single particle gaps here. You know, but when we saw the single particle gaps, you know, very quickly, people that were doing more accurate calculations, like, you know, my colleague Tim Katsiras at Harvard, and my collaborator, you know, the gaps open immediately they saw it, but no other gap open there, you know. So I think, you know, the fact that this, you know, and again, when you in newer devices, this also happens at 3 electrons per Moiré unit cell. You know, 2 you might think is a little bit more special, but actually 3 it would be even harder, you know, for it to be a single particle effect,
But is there
etc.
any specific?
But there are, you know,
signature that it's correlated that you can, you know, or is it kind of inferred in this?
Well, we have, you know, at 2 and -2. Let me see how do I reply to that. You know, at 3, there is, for example, in certain types of samples, you know, ferromagnetism and other things. You know, that interactions are playing a role is very clear. Okay, but you know, the temperature dependence. You know, these are much smaller gaps than these and so on. But of course, you know, it is conceivable that, you know, if there was some doubling, you know, of the unit cell, you know, for example, that, you know, due to some effect, you know, that you would get, you know, this thing, you know, I don't know.
Okay.
Ashwin, if you have an answer, you know, as to what, you know.
Maybe the first part of the question, you know, usually when you do not abandon state, that's a counting mark. It's not very detailed, and that's sort of the, you know, for example, nuclear 2. Now you have 2 electrons per Moiré unit cell. And we know graphene has got 2 spins and 2 valences. So unless there's some symmetric breaking, we've got effectively half an electron per Moiré unit cell. The thing that's actually special and surprising is that 0 you do not get a trivial installer. That requires more in believing the theories to work. But in nuclear 2 and 3, it's even more obvious. Right? And maybe now the best evidence for nuclear 2 being correlated is with STM.
Yeah, I mean, I was gonna say that I would show an STM that, you know, people now, the group of electric designers recently published a marvelous paper looking at the details of the wave functions, you know, and you know, the various there are hundreds and hundreds of, well, hundreds of theories, dozens of models of exactly, you know, what those correlated insulators could be, and now there is detailed STM data eliminating, I mean, almost singling down on a particular state, because the atomic weight function and the weight varies within the Moiré unit cell, you know, is very specific, you know, on the options that you can have on different patterns, and they have been able to measure exactly the patterns for given many body count states for the correlated insulator. Okay, maybe that's indeed the best argument. It's only one group yet, so it's, you know, this needs to be reproduced, but yeah. Steve is going to talk on Friday, I think, about that, yeah.
In the data, it looks like there is some systematic deviation from particle symmetries. This
yes. Yes.
Especially
it's true. It's true. Yeah.
So what are the reasons?
So it's not very well understood. Okay. I should mention that this, which is not electron hole symmetric, although it looks like, okay, is for a particular model. If you do more advanced model, it becomes even more electron hole asymmetric. So at the level of electronic structure already, the system is not particle hole symmetric. Therefore, you wouldn't necessarily expect that it would be particle hole symmetry. However, experimentally the difference is very dramatic between particles. Oh, you can focus on the symmetry, like there's an insulator at 2 and a -2, or you can focus on the fact that many of the things are actually non-symmetric. Okay, it seems like that the difference is larger than theories would naively expect, and it's not very well understood why. Yeah? It's particularly it's much more prominent in the superconducting state and in the compressibility measurements and in other things than this. This actually is about as symmetric as it has been seen, and from there on, it's more asymmetric. Yeah.
Thanks. Can I ask a question about the horizontal scale?
Yeah.
Obviously, if we're dealing with insulators, we're going to have discontinuous bits in the mapping between charge density and chemical potential.
Yeah.
Is this really charge density measured in some independent way, or is it chemical potential converted into charge density via single
This is gate-induced charge density. Means I apply a voltage to my gate electrode. I have a parallel plate capacitor, so I know what charge density I'm inducing in one plate of the capacitor. Okay, we have independent Hall measurements of what the itinerant carrier density in the twisted bilayer graphene is. That thing is not this continuous axis because there are all kinds of phase transitions and things happening in terms of what is, because some charges in the twisted bilayer graphene become localized, etc., etc.
Okay. So effectively, this is chemical potential as applied to the graphene bilayer, but you're writing it in terms of charge density on the plate.
Not even that, because then it would be stretching and doing this, because the chemical potential, when you have a region of high density of states, then it goes fast. This is in an FET transistor, which is the geometry of an FET transistor. This is gate voltage times the capacitance to the gate.
It's electric potential applied to the graphene.
It's electric potential times the capacitance of the state. We call this, and that's the way you report it, because indeed, otherwise, but it's absolutely standard, not only in 2D materials community, but in transistor everything. It's the gate-induced charge.
I've got 2 questions. Is there any good reason for why in old, early devices you see the insulating at ±2 and not the other insulators factors?
So this is extremely sensitive to the specific twist angle as well as twist angle disorder. Okay, in high quality devices, for so we have the most statistics of any group. Okay, for angles less than 1.1, 105, 106, 107, 108, those have higher TCs in general. Okay, peak TC is probably 108. So often we've been focusing on trying to get superconducting devices with higher critical temperature, etc. And then the community has examined a lot of those devices. Those tend to have a very weak insulated state at -2 and a very big superconducting dome. Okay, TC is supported 3 Kelvin. Okay, and at +2, relatively strong insulated state, and even stronger insulated state at +3, which is not shown here. This, I didn't put the twist angle here, but this one is actually 118. Okay, for angles larger than 1.1, particularly 115, 117, 118, the TCs are smaller, and the situation in terms of the insulated state becomes a bit more symmetric. And often we don't see the N equals 3. For example, here we didn't see the insulated state at 3. You see this wiggle? This wiggle is occurring at 1. Okay, so but it's extremely twist angle dependent. Okay, in a way that is not understood yet and mapped in detail. Okay, we're still kind of in the introduction, but yeah, okay. This was supposed to be the beginning. I thought you all knew this. I was going quickly through it.
And is it correct to assume that the charge density is uniform across the C-axis and also target bottom?
Excellent question. Indeed, it's 2 layers. You may think like, oh, I have more density in the electric field goes to the first layer and not so much to the second layer. You can make these devices with a dual gate geometry, okay, so that you can have a purely electric field applied without charge density, or a charge density asymmetric configuration because you apply now gate from both sides, and it doesn't matter. These bands, the flat bands, are the 2 layers are extremely hybridized. Okay, so you don't really. I mean, I'm sure there is some effect, but it's almost not detectable. We have these maps, and all of the features are vertical. It doesn't matter if you apply on purpose a displacement field at the same density, or if you have a density without any displacement field whatsoever. Okay. For crystal bilayer graphene, the effect continues have calculated, the effect is tiny. When you go to 3 layers, however, there you're breaking a special symmetry, which I will measure tomorrow, and it's dramatic. The effect is actually very important. Okay.
We have about 25 minutes.
Okay, let's accelerate a little bit then.
Turbo.
Yeah. So, okay, so as I was going to say, by now we have many dozens, actually probably getting more into the 100 almost devices, but all of this happens between 1 and 1.2 degrees. Okay, twist angle. If you push me, maybe 0.9 to 1.25 or something like that, depends what feature, the decay features, in the tails of the angular distribution. Okay, so then, if you dope a little bit away from these correlated insulator states, you have superconducting nodes, which are electrically tunable. Okay? So magic angle twisted bilayer graphene is an electrically tunable superconductor. Okay. When my students show me this data, the first thing I thought of is the hundreds of times that I have seen data like this. Okay. Let me flip these axes so that they're now in the correct orientation. Okay. So in the cuprates, zero doping means 1 electron per copper atom, okay, per unit cell. You have a multi-insulator, you dope with holes, you have a big superconducting dome, you dope with electrons, you have a small superconducting dome. In magic angle twisted bilayer graphene, you have a correlated insulator of 2 holes or 2 electrons per unit cell. You dope with holes, you have a big superconducting dome. You dope with electrons, you have small superconducting dome. Okay. Now, of course, there's a big difference between these two plots. This is a theoretical plot. This is an experimental plot, right? If you want to realize experimentally, you have to grow hundreds of crystals with different chemical compositions, often different material classes, because you cannot dope everything at all doping ranges or holes and electrons. This is all done in a single device with a single disorder realization in a single cooldown, and I go from here to here in a few seconds. Okay, so that's something which is very different. Now, there are many similarities, but also many differences. Okay, so I don't want to push too much this analogy. Okay. There are many differences between these systems, starting from the basic even structure. Right? There's square lattice, the other one is honeycomb, etc. There are many different topological properties, there are many differences between these systems. Okay, so we posted this in March 2018, and then the theory tsunami came. This is the first few weeks after we posted our paper. I always joke that I used to work in graphene, but no strong interactions. And there, the angular cone of disagreement between theories is about 20 degrees, I would say. In this field is 360. In fact, it's 4 pi's in all directions. So theory started to propose all kinds of explanations for the correlated insulator and superconductivity parameter, with all letters of the alphabet for the symmetry. S, P, D, F, D plus I, S plus P plus D, all combinations, in all orders, real and complex. So we don't know yet the answer, although it's true that the community has started to narrow down very severely the options for the correlated insulators in particular, but even for the superconducting, all the parameter, the options are no longer infinite, they're starting to be narrowed down because a lot of people are doing interesting studies. Okay, so maybe a bit more, the experimental developments, that have happened since April 22, which is when the paper was officially published. So the first thing is that we have reproduced our own results. Okay, that doesn't always happen, so it's good, when you can reproduce yourself. By now, many times we've reproduced our data. This is actually by now very old. We have much more data, but we have now a critical temperature at optimal doping as a function of twist angle, this new knob in this matter. Okay, and you can see that indeed around 108, 109 seems when the maximum TC happens, of order of 3 Kelvin. This is 3 Kelvin in a system which has many orders of magnitude lower Fermi temperature than regular systems. So this is actually the strongest coupled superconductor in the world. Is actually magic angle with the trilayer, not the bilayer. I will tell you a bit more tomorrow. Yep. This is not really an error bar. Okay. When this is a 2-dimensional superconductor, so the fluctuations, the transitions, okay, superconducting transitions are relatively broad, and this error bar is trying to give a sense of 90%, 50%, and TBTK, BKT transition kind of. Okay, that's what it's trying to convey. It's not an error bar.
On-site.
Yeah, onset, middle and bottom. Yeah, exactly. Is 0, 0 is a little bit below 2. Yeah, typically. Yep.
Yeah, about these branket transitions, do they follow something like some of the Graphene?
Yeah, so we have done various treatises of this thing. So in fact, some of these points, the referees were a little bit specific, very peculiar about which model we would use to choose the onset, and we've tried different models. In the end, it doesn't really change much. Okay, but yeah, we've done that.
Also some green dots.
Sorry? Oh, these green dots are, we put them in green because they seem like not too much with the dome, but in reality, these were highly disordered devices. The horizontal bars is a measure of the uncertainty we have in the twist angle. It will be determined through, measuring the lambda Van diagrams. There's a very specific way for which we have to extract the twist angle, and you fit something, but in reality, there can be, if the system is disordered, quite a bit of, uncertainty in the twist angles.
Can you comment on the upturn in resistivity that you see in the gray and green curves on the left?
Oh, here?
Yeah.
Yeah, so these were devices with very small twist angles. So what do you mean by upturn?
Well, it looks like this is about to shoot up before it goes to 0, right? Or am I just not seeing it?
Are you
At the very bottom.
you saying this one or where?
Yeah, it doesn't seem,
I'm not sure about that one,
well, it's saturating or possibly.
Yeah, I mean, remember, this it's enough that there's a region of disorder in your sample which is not superconductive to have a small normal state resistive contribution to it. Okay, so this is this criteria. This wasn't I mean, many of these curves are many of these data points. Okay, but this is probably that one is one of these which is below 1 degree and it's barely there. Okay, so don't this thing, again, is electrically tunable. And for example, as you get close to the correlated insulated state, you have sometimes a drop, which then at very low temperature increases. This is all in the original paper also. We analyzed that to some extent. In fact, some people have told me that is a signature of various things, including silver, etc. And the underdog. But yeah, I haven't thought about that particular curve. Okay, so better than you reproducing your own results is when other groups independently reproduce your results. Okay, only then is real science. Okay, when other groups reproduce it, and luckily for us, many groups have reproduced our results. Okay, and in particular, the first one to do so were collaboration between Corey Dean and at Columbia and Andrea Young at UCSB. Not only they made a device at the magic angle and they saw the correlated insulators and they saw superconductivity. Then they made a device of the magic angle at 1.27 degrees. Okay, they did not see correlated insulators, they did not see superconductivity, but what they did there is they applied pressure to it. And since the magic angle condition depends in interlayer tunneling, this interlayer tunneling is affected by the pressure in the system, and they could apply the pressure needed to reach the magic angle condition. Okay. For that particular twist angle, and then they saw superconductivity. Okay, so that was a very interesting study that really, pinpointed, what we knew that it was associated with these flat bands, with the magic angle condition behavior. And then the group of Dimitri Efetov, a few months later, they also, extended, to other superconducting domes, etc. And by now, many groups have reproduced all of this. Now, we have seen plenty of phenomenology characteristic of quantum materials, for example, strange metal behavior, pneumaticity, permutation constructions, cascades of phase transitions, pseudo-gap physics, all kinds of things. Okay, I mean, seen the system. This is, for example, as in the cuprates, this is the biggest wedge here in this picture is a strange metal phase, which is characterized by strange behavior, hence the name, okay, of many properties. For example, a very characteristic one is that the resistivity is linear in temperature all the way from very high temperatures down to very low temperature. Yeah? Usually you expect quadratic at low temperatures. So this is data from magic angle to bilayer graphene, as you can see, and as soon as you get out of the superconducting state, the resistivity becomes linear. Okay? You can choose a sample or tune your density in your dome so that TC is much lower, and then it goes linear down to very low temperature. Okay, and in fact, recently in this version of the talk, I don't have the reference, but the group of Dimitri Efetov have shown that this behavior here it went down to 0.5 Kelvin right before it became superconducting, the group of FFF has been able to show that it can go down linear down to 40 millikelvin. So it's, magic angle twisted bilayer graphene is one of the strangest metals, if you call strangest by how low in temperature it goes linear. Okay, yeah.
How far up?
So it goes a bit more, maybe to 40, 50 Kelvin, something like that. Okay. Now you have to remember this system, the Fermi temperature is this, 20 Kelvin, more or less. Okay. So it's the equivalent of going up to several thousand Kelvin in most materials, but there are those single particle gaps. So at 100 Kelvin, you are exciting carriers into those extra the remote Moiré bands, and those have very high mobility and stuff. And therefore this thing bends downwards rather than how it bends downwards because you start conducting very well through the remote bands.
So the question is about multi-operator limits, and you say that would be shortened by some other areas that were.
No, so actually, depending on whether you use the 2 pi or not on the module Ferrari limits, we have already gone well past it in some of our devices, but we're still within a small factor before we reach that going down. But that going down, because we can do these maps as a function of density, we know as we're filling closer to the band edge, it gets more easily excited into those regions. So we can see how proximity to the band insulator is giving you transport at high temperature and the resistance bends down more quickly. So it has like an obvious interpretation. Okay. Okay. So we have discovered many other correlated systems in smaller systems. Okay. The second one maybe was ABC trilayer graphene aligned to hexagonal nitride. Then several of us did magic angle twisted bilayer graphene. So bilayer graphene with zero angle, you put them on top of each other at the magic angle. Okay, and that system also shows correlations, interesting magnetic states, no superconductivity, very different from magic angle twisted bilayer graphene. You also have the Moiré transition method and chalcogenides, etc. By now we have many Moiré systems exhibiting very rich behavior. And very important discovery was the discovery of ferromagnetism, anomalous Hall, and even the quantized anomalous Hall effect, which brought the role of topology front and center, to this problem. So, in fact, one of the nice things about this field is that it has meant the merging of several condensed matter communities, which did not interact that closely before. For example, the community that did 2D van der Waals materials, PIN and other materials, like myself. The people that get strongly correlated or have strongly correlated materials, cuprates, pnictides, heavy fermions, etc. And the people that do topological condensed matter physics, integer and fractional quantum Hall physics, topological insulators, Weyl semi-metals, all three, come together in this field of Moiré quantum matter, because structures have pieces of every, each of these communities. So I, get to enjoy and talk to many more people now than I used to. In particular, the role of topology, early work, within a couple of months or a few months of experimental discovery, people doing theory realized, other interesting topological structures. And together with our collaborator Senthil, we even went, and calculated, near reflection bands in various types of Moiré superlattices, depending on which one superlattices, Chern numbers, and X variation with twist angle, all these things. And within a few months of publishing this paper, the group of David Gordon showed this very strong, very large anomalous Hall effect on magic angle twisted bilayer graphene aligned to hexagonal barrel nitride. And then 6 months later or something like that, the group of Andrea Young showed the actual quantized anomalous Hall effect in the system, again, in magic angle graphene aligned to hexagonal boron nitride. Okay, and also was seen later in ABC trilayer aligned to HBN. Now in transition metal like chalcogenides, Moiré structures, it has been also seen, and it's in other systems. Yep.
So how important is it not for?
Yes. So of all the effects, okay, in magic angle magic angle graphene, this is the least reproduced one. And by which I mean one device at Stanford, one device at Santa Barbara. Each of the groups has tried many times to reproduce their data. They haven't. We all think this is real because 2 independent groups did this, okay? But none of them has been able to reproduce their own data ever. And no one else has been able to reproduce their data ever. So my own group, we have tried, okay? we do not know. Now you have two pieces. You have the magic angle graphene, you have to get that angle right. And then there seems to be an angle that you have to have with HVN to get this thing, which is not zero. Because we've tried with zero many times, and we didn't see it. Okay, I'll show you tomorrow what we found out instead. And but so several theories, Santil, Alan McDonald, etc., have said that if what you want to have is a matching of the the graphene HVN Moiré pattern is also 13 nanometers at 0 degrees. Okay, it's by chance, same as magic angle, but they're rotated with respect to each other. So if you want to have sort of a matching of the Moiré patterns to maximize the symmetry breaking of the Moirés, you probably need something like 0.6 or 0.8 degrees between the graphene and the HVN. So now you have to get two angles right, the 1.1 and the 0.6 or 0.8. And we're not sure if that's why people are not finding it, because it's much easier to aim at 0 than aim at 0.8 for the graphene HVN. So the whole community is a little bit like, what's going on? Why is this not reproduced? Okay. But there will be surprises in the coming months. I will be able to tell you about some of these things. Okay. Other developments are happening, which I can tell you right now about, but which are magnetism and then large anomalous Hall effect is real, and it will be much more prevalent and reproducible in the near future. Let me put it this way.
Until the last 10 minutes.
Yeah. Okay. Okay. So lots of local probes have been used now, which gives us microscopic, visualization of what's going on with these Moiré patterns and so on. Okay. It started with scanning telemicroscopy, but also scanning nanosquids, scanning single electron transistors, scanning near optical microscopy, scanning transmission microscopy. Now there is even something called the quantum twisting microscope. So let me highlight two results. One is that paper that Ashwin mentioned, and I also mentioned of from the group of Ali Yazdani. I think this is already published in Nature, looking at the details of the atomic scale wave function and their variation within the Moiré unit cell that really narrows down, in fact, in many cases, pins down exactly what is the many body ground state of the correlated insulators. Okay, this is really, usually STM do work and on a section of a few 10 angstroms. These guys have to do over several Moiré unit cells, detailed atomic scale, STM studies and investigations of the wave functions and their energy dependence with gating also and so on. This was really a beautiful. And an extremely interesting development is the group of Jarillo-Herrero, even Ellis is a collaborator on this paper, co-author of this paper. They demonstrated that, when we put graphene on graphene, we can choose any angle that we want, but that's it, it's fixed, okay? The group of Jarillo-Herrero, what they did is they put one of the graphene sheets on an AFM tip, the other graphene sheet at the bottom, and now they can come on top of it and touch at an angle, and in situ, rotate the AFM tip and measure the properties as a function of twist angle continuously, okay? That's why it's called the quantum twisting microscope. They haven't gone yet to the magic angle. There are some technical difficulties to reach the magic angle doing this thing, but they have done a little bit larger angle. So you're looking here at what is the electronic structure of magic angle, of twisted bilayer graphene, okay? Because they can measure, they can do like RPES, but with an AFM tip, because they can measure the interlayer tunneling, and map the band structure and function of momentum, using this thing. So, and they can apply pressure and they can do many things, they can apply a magnetic field, of course, they can do many, many things. This is really fantastic. And I know several groups which are trying, to build this quantum twisting microscopes, It's the first time that this can be done continuously in this manner, So it's really a fantastic development. Okay, now, we're building the next generation Moiré quantum matter, Moiré Magic 3.0 and beyond. I will talk a little bit about this tomorrow. So Moiré Magic 3.0 means 3 layers, okay? The group of Philip Kim and my group published, a couple of years ago, back-to-back papers the same week, showing that magic angle twisted tri-layer graphene, okay? I'll say more about it tomorrow. It was theoretically predicted, by Ashwin and his collaborators, the angle. Magic angle twisted tri-layer graphene is an extremely tunable and very strongly coupled superconducting system. It's even more strongly coupled than the bilayer counterpart, okay? And then last year, Moiré Magic 4.0 and 5.0 happened, which means that 3 groups, the competition is very big in this group. We post something, and that same week, 2 other groups post, a group of Stefan experts at Caltech, my group, and also a group of Tutuk. We all 3 showed that 4 layers and 5 layers also, again, choosing angles predicted by Ashwin, are also superconductors. So this is a family of robust superconductors. I'm pretty sure if you do 6, 7, 8, which the angles are also calculated, they would also superconduct. Because in fact, the superconductivity becomes more prevalent and easier to find the higher the layer number. 5 layers, 100% of the devices superconduct and so on. So, okay, so now, okay, so I'm going to skip this. I want to show you the outlook, which is only a couple of slides, but I'm going to skip this. I'll talk about ferroelectricity tomorrow. Yeah. So, yeah, the correct insulator, the problem is that when you add more layers, I will talk about this tomorrow, you start to have Dirac bands that appear in the electronic structure that short circuit your system. You have whatever is happening with the flat band. When we have signatures that indeed in the flat band, there's still the correlated insulator, but you have a highway of electrons, these Dirac electrons, which are flying through, and therefore the short circuit. So you don't experimentally measure an insulator because you have Dirac band. Okay? So let me, in the interest of time, skip through this, which is it's nice, but it's a simple, effect, although it's attracting enormous attention in the engineering community. But let me actually show you this, because this, I think it's nice to see that there, So I showed you all of this, it happens, this is all done using graphene and maybe graphene and HBM, okay? You can get a lot of similar physics, not superconductivity yet, but a lot of similar physics also using transition method and chalcogenized semiconductor twisting structures. But, we have hundreds of 2D materials that we can twist on top of each other and try to explore, right? So you can imagine now many, hundreds of theories are just trying to find magic angles or not, or what happens when you twist all of these, quantum magnets or electric superconductors, which are by themselves 2D, okay? And then you can twist them on top of each other. So some of the most exciting predictions include, high temperature topological superconductivity when you twist double layer cuprates, okay? In twisted double layer cuprates. You can also have Moiré magnet. We have 2-dimensional crystalline magnets. When you twist them on top of each other, often the magnetism depends on the stacking, and when you twist, the stacking changes in space. So you can have, Moiré skernions, Moiré magnets, and all kinds of things. Okay, and some of these are beginning to be realized experimentally. Now, beyond twist electronics, the cold atoms community are starting to twist the optical lattices. Oh, wow, why not? Let me do this thing, okay? So first it was theory, and there's several theory papers, but now in China it has been done experimentally, twisted, cold atoms optical lattices, okay? The people that do phononics, whether it's classical phonons or quantum phonons, are also twisting them and predicting what will happen. This trick of slowing down the Fermi velocity works for anything, particularly slows down the phonon velocity too, and you don't have magic angle conditions for stopping your phonons, etc. Okay, so you get these things like magic angle by the phononic graphene, etc. Perhaps the fastest developing one is the photonics community, because people are doing more twisted photonics. You can slow down tremendously speed of light. Okay, so this is actually, there are entire programs in the US now dedicated to this, and many groups are actually working on this, because you can get all kinds of nonlinear optical effects, etc., by using twisted optical, photonic or lattices. Even more, these regions of A stacking, etc., very high density of states, this can be very useful for electrochemistry and catalysis. Okay, so there are quite a number of groups, doing experiments and theory on more electrocatalysis, more metals for various, electrochemistries, etc. And last but not least, at least there is one paper, I should investigate there are more, talks about Moiré gravity. Gibson Galitsky published this paper where apparently in twisted layer field, you can realize, black hole physics, etc. I don't know, who knows. So with this is the end of part 1. I want to thank, my graduate students, plenty of collaborators, some of them here in the audience, funding agencies. I'm glad we can get back together the way we used to. And you can ask me more questions, and tomorrow will be part 2. So.
Yeah, really cool talk, but we're seriously into coffee time. So in the interest of time, any quick urgent questions now, but other ones, please ask during coffee or tomorrow. Any quick urgent?
For all those materials that you presented very quickly at the end of your talk, are they all starting with a single layer and then twisting?
Yes, yes. It's all single layer and twisting when the layers are identical, like you're saying, because you have to form a Moiré pattern. If the layers are not identical, as I will show tomorrow,